So the next speaker is Mr. Ramanujam. He's a computer scientist and he's also involved in Tamil Nadu Science Forum and lots of other things. Okay. He will be talking on playing games, mathematically speaking.
Good afternoon. Yeah, so as advertised, my name is Ramanujam. I work in this institute. After all this fancy flights into axiom of choice, this is going to be more mundane. And so I gave the title Playing Games and Mathematically Speaking. So the exercise is going to be for you to find out where is the mathematics in this. I don't see any obvious mathematics in what I'm going to say, so you have to tell me. Okay. So it's about playing games, so we'll start with playing a game, of course. So okay, so very basic game to start with. I need somebody to play with me. Will you please? What's your name? Chandni. Yeah. Okay. So tell me a number between 1 and 10. Okay. So I'll pick a number within the next 10 numbers. We can go on like this, but there needs to be some objective, right? There's no fun in just going on picking numbers. So the rule is whoever first reaches 100 wins. Okay. So you said 19, I said 20.
You say, sorry?
20.
29,
29. 30.
35,
36.
42,
52.
59,
60.
68,
70.
75,
76.
85,
89.
99,
100. Okay. Thanks. Yeah. So, would you like to start? What's your name, please? Janani. Would you like to start or would you like me to start? Yeah, please.
1,
2,
3,
10,
15,
20,
25,
30,
21,
40,
45,
46,
50,
51,
55,
60,
70,
71,
79,
89,
90,
100. Okay. Yeah. So, would you like to start or would you like me to start? What's your name? Praveen. Yeah. Why don't you start? Or would you like me to start? You want me to start? Okay, 5. 10.
20,
30.
39,
39. 40.
40,
No, I said 40.
52,
Yeah, you can only pick in the next 10 numbers. 50, right? 51.
60,
61.
70,
71.
74,
78.
79,
89. You should resign at this point, right? Okay, so it's clear, right? It's clear that anyone who hits 89 is going to win. Why? No matter what the other numbers your opponent picks, you can always come back with 100. So it's clear that to reach 100, it suffices to reach 89. But then what's the next step? Somebody should tell me what is the next. What should I write next out there? To reach 89, it suffices to reach well then, go on. To reach 78, 67, and then 56, 45, 34, huh? 23, 12, 1. So, whoever starts has a way of winning the game. So, I would say for this, so is it clear that whoever starts can always win this game? Why? Because supposing you politely ask me to start, I say 1, right? Now, no matter what numbers you say, I can always say 12, right? And then no matter what numbers you say, I can always say 23, right? And then so on, right? So, the sequence 1, 12, 23, 34, 45, 56, this sequence constitutes a winning strategy. For player 1, whoever starts. Who is player 1? Whoever starts. Where there are 2 players, so whoever starts will call player 1, other player is player 2. How did we arrive at this winning strategy? We said, okay, to reach 100, you have to get to 89. So this thing is called backward induction. Backwards induction. I am just putting it in quotes. There. It's just terminology, but it's useful terminology. Why is it backwards induction? You're doing some kind of induction, right? You're saying to do this, this is what I should do earlier, and you're working backwards, right? Have you seen so-called endgame problems in chess? Have you heard of? If you have not heard of it, I would advise you to take a look at it. It's a lot of fun. There are a lot of chess puzzles which are of this form too, where you really have to work backwards to figure out what is going on. And here is an example of what we did was backward induction. But there is a notion that is interesting here, and this is really what I am interested in. This thing is a strategy. What's the meaning of the word strategy here? A strategy is something that what? Yes? Yeah? A plan. Think of it as a plan, right? So what kind of a plan is it? How do you use a strategy? Okay. In general, when you're playing a game, certain moves are available to you, right? You can make, when you're playing chess, you can move the horse or the rook or the minister, whatever, whichever. Right? Now, at a time, at any position of the game, you've got several moves available to you, and you're picking one of them. Right? Now, on what basis do you pick? Right? When I tell you 17, and then you say 20, right? What are the choices available to you at that point? My having said 17, what are the choices available? 18 to 27. You can pick any one of the 10 numbers, and the method by which you pick is what you can call your strategy. Right? If you have a plan, you follow a particular plan. Now you can say, okay, I knew the winning strategy, but then I was always doing a +1, for instance, right? Or I was doing going to the nearest round number, nearest multiple of 10. Right? You say 25, I say 30, you say 35, I say 40, like that. Why? Just to confuse you, if I can, right? So the idea is that, of course, you want a strategy. A good player is one who picks a strategy which the other guy cannot figure out. Right? Of course, if you know what my strategy is, then you may in this case, there is no counter strategy. Right? If I follow that sequence, you are dead. Right? If I do 1, 12, 23, there is nothing you can do. Right? Now, that is what is called a winning strategy. Among all the possible strategies, right, you can have many strategies. Right? One strategy is, whatever you tell, I will pick +1. That's a strategy. Right? I respond with +1. I respond with +5. It's a meaningful strategy because it tells me, it gives me a function that I can apply every time, right? It's a dependable strategy, but it may not be winning because in the process of doing this, you hit 89 and then my strategy will not help, right? Okay. So a winning strategy is one where no matter what the other player does, right? In this case of two-person games, right? No matter what the other player does, if I follow that plan, I'm guaranteed a win. Right? So now there are all these names coming in. There are terms coming in like player, rules, strategy, win, lose, all this is happening. So this is the sort of thing games are about, right? I'll say a little more about that, but after, maybe doing one more game. Okay, here is a game. So what we have seen is an example of a two-player win-lose game is what we have seen, right? Because we had two players and it's a turn-based game. This is all terminology, and let me just give you the terminology for now. So what we saw was an example of a two-player turn-based win-lose game. Why do you say turn-based? Because the turns strictly alternate, right? And we know games where it doesn't strictly alternate, right? When you play cards, okay, you play, if you get the trick, you play again. Otherwise, if you lose, it passes on, right? You can do many such. So this is an example of a turn-based game, and it's a win-lose game because there is a clear winning condition, right? One of the players wins, exactly one of the players wins, right? Both cannot win, and there is no win-win and lose-lose and all this kind of stuff here, right? It's a win-lose game. Okay, so here is another example, and okay, so here I think of a two-digit number. Again, very childish stuff, right? So I think of a number between 1 and 100. So you should find out what that number is. How many questions do you want? 7, huh? Can anyone do it with fewer questions? 21. Come on, you're saying 7. I'm not going to listen to 21. Anyone who says 3? 4 questions? Anyone with fewer than 4? One question, yeah? Surely. Yeah. What is the question? What's the number? I'll tell you, right? Come on. I just said I thought of a number and asked me a question, right? You ask me, I'm an honest person, I will tell you the number. What's the problem, right? So if we make it more interesting, right? Obviously. So I'm not going to, allow questions of that kind. So the thing is that you can ask me whatever question you will like. I don't care. I'll only answer yes or no. So of course, if you ask me what is that number, it's useless because I'm not going to answer yes or it's not a yes/no, right? Now, how many questions? Yeah, okay, 7. But somebody says 7. I want somebody who can do it fewer questions. 5. 5. Okay. So she's ready for 5. Anyone for 4? No. No, that's not a dependable strategy, right? You need some strategy, right? Okay. Anyone now? Anyone with 5? Yeah? Would you like to try with anyone? No one is willing to try. Yeah? Anyone for what? How many would you need? See, surely with 99 questions you can always find it. That's for sure, right? 99 questions suffice because you have eliminated 99 of them. In the worst case, you got only 1 left, so no problem, right? Okay. So, how many would you need? How many questions would you like to? Why don't you try? Ask some question, let's see. Yeah. I have the number. Is it? Is it between 0 and 50? Yes. Is it odd? There are 2 questions there. Is it odd? Is it a prime number? No. Yes. 3 questions. Right. Okay, I am willing to. I follow. You set the rules of the game, I'll follow it. No problem. Yeah. So what have we got so far? You know it's between 0 and 50, and you know it's an odd number, you know it's not a prime. Okay, now? Who's asking? Is he allowed to ask? I mean, you have to help her. So, it's okay, no problem. Yeah? Is that question okay? It gets counted, right? So, the question was, is it a multiple of 3? Is it legal? You have to work it out with her, you see. So, she's the one who's... Yeah? Yeah, what's the next? Yeah, the clock is running. Is it 1? No. Is, huh? If that's a yes no question and the answer is yes. Okay. Who's asking? Is he allowed to ask? You're the one who's to. Hmm? She seems to, yeah. Huh? Is it greater than 25? Yes. Wait. Huh? She has to okay every single question there, right? No, but then you didn't okay his question. He had a question there. What is that? Is it a multiple of 3? Yeah? Shall I answer him? Okay. No. But already, you have gone to 6 questions, so... Yeah? Less than 40? Yes. Well, okay. I'm going to restart. There are too many. You've been... I want to take you later. I know why. Huh? Okay, so... I've thought of a number. Start. Is it odd? Yes. So one question. Keep track, no? One question, yeah? Is it less than 50? Yes. Is it a multiple of 3? No. Yes. Yes. No. There are 7 questions already. No, 6, yeah. Yeah, 6. That's true. You've already counted 6, yeah. So what are the numbers left? What are the numbers left right now? So how many more questions do you need? Why don't you? Yeah? What is the question? Is it 40? No. Well, you have the mic. Yeah? I said you have the mic. So. Yeah. Okay.
5 questions.
5 questions. I think I'll take that bit there. Yeah. Is it greater than 50? Yes. Yes. Greater than 87? No.
Greater than 81.
No. You have only one question left. What about, can somebody else advise him now? Do you think he should continue or resign? What are the numbers left right now? 76? 80. So there are 5 or 6? 5 numbers, okay. Okay. And he has got only one question. So can he find out? Okay, let him try. Huh?
Is it odd?
No. But your 5 questions are over.
This was last.
No. Right. Okay. Anyway, you can find it. But there is some strategy here. What was the strategy that was going on here? Can somebody say? What happens? Well, okay, you are halving. So that something is about that, right? You are starting, you are looking among 100 numbers. Right? What is the first question? Is it greater than 50? Greater than or equal to 50 if you like. Now, whatever answer I give, right? Whether I say yes or no, what is going to happen? The space that you are searching goes from 100 to 50, right? So it doesn't matter what answer I give. So this is no and this is yes. Could be the other way, doesn't matter, right? Now, this I will call an efficient question because you could also ask, right? I mean, for instance, you ask, is it a multiple of 3? Or let's say there is a question, right? Is it a prime number, right? Now, that's also a question, but what's the difference between the question, is it a prime number and is it greater than 50? Yeah, in the case of, if it's a prime number, you ask, is it a prime number? If I say yes, you hit the jackpot. You hit the jackpot because there is only a small number. How many prime numbers are there between 1 and 100?
20.
Huh? 25. Yeah, you go and find out, right? Okay. Now, but the thing is, if I say no, you got a large set out there. You could also ask, is it greater than 10, right? If I say no, it's great because you've got only very few numbers. But if I say no, you have brought it to 90. Doesn't help. Other one, is it odd? This is a favorite question. Is it odd or even, right? Now, that again brings it down from 100 to 50, but it's not as good as this because this gives you some visual feel, right? You are narrowing the interval in some way, right? You know, if it is distributed, you know, it could be a little more, but it's okay, it's equally good. But it's clear that with one question, you can bring it down from 100 to 50. Is that clear? With one question, you can bring down the search from among 100 numbers to 50 numbers. So then with 2 questions, you can bring it down to 25. Is that clear? Because no matter what answer was given in the first one, supposing I say yes, right? With one question, you can bring it down to, say, let's say greater than 50. I say yes or no, it doesn't matter. Whatever this thing I give. So again you ask a question, I say if your question equally divides the space, right, I can always bring it down to 25. So with 2 I bring it to 25, with 3 I bring it to 13. Okay, so that is where you have to be careful. With 4 questions I bring it down to 7. 5 questions I bring it down to 4. 6th question I bring it down to 2. 7th question will get me the answer. Is it clear? Right? That boundary case is a problem and that's important, right? And that's why you were saying 5 and I saw some hesitation there, right? So it's clear that with 7 questions, you have a strategy to find the number. Is it clear? Is it clear? Once again, you can always ask, is it greater than 50? Supposing I say yes. You say, is it greater than 75? I say yes. You say, is it greater than 87? I say no, and so on. Right? You can divide it up and ask. With 7 questions, you have a strategy. Definitely, no matter what answer I give, you can find the number. Now is the other way. So it's clear that 7 questions suffice for you. Is it necessary? Maybe with 7 questions you can find it using this strategy. Maybe a completely different strategy will let you find it with 3 questions. Is it possible? What do you think? Yeah? What do you think? Yeah. Give me a strategy. Oh, you think there is a strategy except that you can't find it. Depends on luck. But that's not a strategy. You see, I want a winning strategy. What did I say was a winning strategy? A winning strategy is one, no matter what answer the other player gives, is sure to get me to win. Right? So, but here this is not win-lose. So that's why I'm moving away from a win-lose game, but it's a game nevertheless. But the point is that you want to ask with as few questions as possible. Right? You want to find out. Now the question is, with 7 questions you have a strategy. Do you have a strategy with 3 or 4 or whatever? Right? You're saying it depends on luck. Now, is there some way by which, without counting on any luck whatsoever, you can find out with fewer questions? Let me ask the other way. So this is a 2-player game, right? You are trying to find out with as few questions as possible. What is my objective? To make you ask as many questions as possible. What strategy do I have to force you to ask 7 questions? I know that you will find it with 7, because remember, as soon as we started, these guys were yelling 7, 7 and all. So I knew that somebody was going to find with 7 questions, okay, right? Now, what is my strategy? Strategy, but what moves I have got at all? What is under my control? The number that I think of. That's the only choice I have. In this game, the moves for you are picking questions. Once you ask me a question, I have to answer. There is no issue. So the only choice I have got is in the initial move, right? It's clear? I have among 100 numbers, I have some number to pick. That's my choice. So what number should I pick so that you're forced to ask 7 questions? What is not a round number? I think all numbers are round. Whole numbers, yeah? Whole numbers are all round. No? So why shouldn't I think of 50? I mean, I like 50. 75, I like 75. What's wrong with thinking of 75? How do I know you are going to ask is it greater than 75, right? Okay, maybe I should think of 45. 45 is a good number. What's wrong with that? Yeah? So what number should I think of? What's your guess? What number should I think of? So that you're forced to ask 7 questions.
It will be like 100 by 25, 375.
Yeah, but powers of 2 didn't figure. Eh? Your first question was, is it greater than 50? So that is not a power of 2. In fact, there was no power of 2 in your questions at all. It is all 50, 75, 87.
100 divided by power.
100 divided by, well, I don't see. Yeah? What's your candidate number? What do you think I should think of? 1? Well, somebody asked, no? Did you? Someone asked, is it 1? Right? You asked, is it 1? Right? Now, I'm an honest person, right? If I have thought of 1 and the first question she asks is 1, is it 1? I'll say yes. So I have not. But that holds for any number, isn't it true? Think of 87. Suppose I think of 87, right? Or 87, 83. First question you ask me, is it 83? I'm dead. Is it clear? So, in fact, if I think of any particular number at all, I have a problem. So what is my strategy? Don't think of any number, right? And I am not cheating, right? My strategy to make you ask 7 questions is not to think of any number. So what do? I wait for you to ask me a question. If you divide it equally, right? For instance, if you ask, is it greater than 50? What should I say? Doesn't matter. Toss a coin, say yes or no. Just keep track of the answers you give. That's all, right? And she put me in a spot at some point. Did you say is the multiple of 3? Did you say yes or no? No. I have to remember all this stuff, right? Okay. Yeah. I was hoping somebody else was keeping track of all that, right? And so that's all you need to. But if you ask me, is it a prime number? What answer should I give? I would be stupid to say yes. I should say no, right? I mean, there is this classic problem, right? So there are two people, two of you, and I bring a cake. And I say, share it equally, right? How will you cut it? I mean, suppose she comes and cuts it. You're not going to take it, right? Because she's not going to, give you in. So how should you cut it so that you can be sure that, you get whatever you want? Yeah? One cuts and the other chooses, right? So why does that work? Because if you cut it into unequal pieces, what will happen? The other person has first choice, right? Exactly the same principle, right? If you ask me a question that divides the space unequally, right, I'm going to take the larger piece of the cake, right? So if you ask me, is it a prime number? I will say no, for sure. So my strategy is only that. I wait for you to ask a question. I know that with a yes, no, you are going to divide the space into two subsets. If they are of unequal size, I give the answer that makes the game go on with a larger set. If it is equal, the best you can do is to cut it equally, in which case I'll just answer randomly. And I keep on going, and then I know that you must ask 7 questions. So here is a situation where 7 questions suffice for you to find the number, and I can show that I have a strategy, you have a strategy to find it in 7 questions, I have a strategy to force you to ask 7 questions. A game theorist would call this in equilibrium. Okay, it's a nice term, and basically quite a bit of game theory is about studying things. You call this an equilibrium because you don't have any reason to shift away from this, I don't have any reason to shift away from this, this is what we would do. Okay, computer scientists call these things upper bounds and lower bounds and so on, right? So the 7 is an upper bound for you. Number of 7 questions, and it's also a lower bound.
I have a doubt.
Yeah.
So, strategy, whatever number you think of, basically it will take 7 questions to find that number. No matter what number you think of.
No, that's okay. So this is the thing, right? All I'm saying is that you have a strategy. This, if you follow this strategy, right? Divide and conquer or binary search or whatever you can call this. If you follow that strategy with 7 questions, you're sure to find it, right? And now what I'm saying is, I have a way of behaving, right? I have a way of giving input to the game, which is thinking of a number in such a way that you're forced to ask 7 questions.
What I'm saying is, whatever number you think of, I'm forced to ask 7 questions.
If you want to, if you do not want to depend on luck, that's why it's a lower bound, right? Right? My strategy is, I will not think of any number. Whatever question you ask me, depending on how you've divided it, I'll give that answer.
So the goal of your strategy is to force me to ask
7 questions, at least, yeah. Of course, if you ask more, I'm happy, no problem, right? So think of it this way. Okay, so this as a game, you can think of, in the previous game, we had a winning condition. One person wins and the other person loses. In this game, there is no win-lose. This is not a win-lose game. This is what people would call a game with payoff. Okay, the payoff I get is the number of questions you ask. So the more questions you ask, the happier I am, right? So all I'm saying is, I can be sure of getting a payoff of 7, and of course I would love to get more. And what about you? What is the payoff you get? It's the negative of the number of questions you ask, right? So if you ask 10 questions, you get a payoff of minus 10. I'm sorry that you get only negative numbers, but I hope you like negative numbers, right? So you want to ask as few questions so that you get as much as possible. So the best you can hope for is minus 1 question, right? And I would love to make you ask 99 questions, so I get a payoff of 99. So 7 is in equilibrium here. This is what game theorists talk about. Okay, so this is also fun, and this idea, right, is something that runs through many games, right? And let me give you a flavor of some slightly different thing, but maybe make a remark and continue with one more game, and that's it. Okay. So this idea of backwards induction, right? I started drawing that picture like that. So in general, in a game of the kind that we have been doing, you start with some game position, and in the guessed, that reaching 100 first, the initial position was whoever where we start, and somebody picks a number, right? You have a choice of several numbers, and then you are in a new position, several numbers, and so on. Now, you go on like this, at some point you reach the end. This is called a tree, and this is what you call the leaves of the tree, where you end. Now, it should be not very difficult to see that the game that both the games that we were talking about can be drawn using a finite tree. This is a tree written perversely upside down. The root is on top and the leaves are below. Well, mathematical trees tend to be perverse like this, that's all. But there is a well-defined root, one unique game position, and then you go down, right? Now, this backwards induction argument says, right, what is the argument that we gave? To reach 100, it suffices to reach 89, right? So you started from the leaves and then, okay. So you are saying, okay, here we are. Here is a leaf where player 1 wins, here player 2 wins, here player 1 wins, right? If this is the end position that you reach, player 1 wins, here player 2 wins, etc. Now, this could be a way by which you have written the win, or it could be something of this kind where you end and say that here player 1 gets payoff, what is that, 99 minus 99, 8 minus 8, 15, by which I mean you ask 99 questions. So I got a payoff of 99, you got a payoff of minus 99, right? Or you ask 7 questions and you got a payoff of minus 7, I got 7, right? So such payoffs are what are called zero-sum payoffs, because the sum of the two payoffs is 0. But it's a more general thing than saying who wins, that's all. Now, in general, when you got a situation like this, now you say that, what was the previous position? The previous position, somebody made a move, right? It must be player 1 or player 2, right? Supposing it was player 1's turn, right? Now, player 1 has control over what happens now, can pick a move. Would player 1 pick this move? Well, if you are stupid, you might do it, but if you are thinking of what consequences there are, you realize that if I pick this move, I win. If I pick this move, my opponent wins. So I would rather pick one of these, either this or maybe this. So in any case, if play reaches this point, you can say that player 1 has a strategy to win the game if I get here, because I can always pick. Right? So I can say that player 1 can win this position. Right? If, for instance, it had been the case, this is player 1's turn to move, 1's turn. But in all of these situations, player 2. Then it doesn't matter. No matter what player 1 does, this is the position that will be 2 wins this position. Because no matter what move player 1 makes, 2 is going to win the game. So what you can do is, starting from the leaves, right? You can go one level up and see who wins. Now, of course, you can do that. You can keep going up. That's what is called backwards induction. So you can keep going up all the way, and it's a finite tree. So what will happen? At some point, you will hit the root, right? And at the root, you will say player 1 wins this position or player 2 wins this position. It doesn't matter. So you are able to determine. So this little argument, very simple argument, you can sit and formalize and show induction and show that no matter what is the size of the tree, however deep your play is, you are going to, one of the players is going to have a winning strategy. Now this is something attributed to Zermelo in 1930. This is a theorem that's going to celebrate a century next year, the centenary of this theorem, and it's an extremely interesting theorem. It says every finite tree like this, right? Every finite game, two-player win-lose game, every finite win-lose turn-based game is determined, it says. Determined means one of the two players has a winning strategy. Now Zermelo was interested in proving this theorem for a particular game, which we all like. What is that? Chess. Chess is a two-player game. Win-lose, you can, there are draws involved. So for the moment, let's say that you can only win or lose, there is no draw. You can change the game, just a little, definition just a little bit too. Say, instead of saying determined to mean that every player has a winning strategy, you can say every player has a non-losing strategy to not lose, so that either win or a draw. But let's not worry about it for the moment. And it's a turn-based game. And think of chess as a game tree. The chessboard that you start with, that is your initial position. Player white moves. How many moves can the player white make? Some finite number, right? And then there is a new board. Black can make one of finitely many. You keep on going. What can happen? You can have a loop, because I can keep moving my king like this, you keep moving your king like this, but that's ruled out. If you actually think about tournaments, in tournaments this is ruled out. In fact, all tournaments make sure that you can't repeat a position. In fact, if you repeat a move in many tournaments, you have to resign, it becomes a draw. So, okay, forget that. But it's very easy to rule out loops so that it's a finite tree. So, Zermelo's theorem, which as I said, you can sit and prove, it takes 15 minutes for you to set it up and prove, assures you that the game of chess is determined. Determined means what? Either player white or player black has a winning strategy. If only we knew who, right? We still don't know, right? So this is a theorem that's very interesting, because mathematically it's very interesting, because it says there exists a winning strategy for one of the two players. Till date we don't know, we can't find out, and it's very easy to calculate how much time a computer, why should you figure it out? Ask a computer to figure it out, right? But then the size of the tree, size of the chess tree is humongous. You know how many nodes there are there in these little circles that I have drawn, right? What is your estimate? How big is that? Well, something to the power of something, why don't you say like that, right? At every move, how many moves can you make, right? There are 64 positions, right? 8 by 8, right? Now, this is huge. You can sit and calculate, it's somewhere around 2 to the 150 or so, right? Now, 2 to the 150 is a huge number, right? Now, so even if you think of super duper computer technology which will sit and analyze the whole tree, you've got a long way to go, right? So, it's not clear that just because somebody comes and tells you that there exists a strategy for one of the two players means that you will find it. Okay. So so this thing gets very interesting. You can ask like actual games, how do you compute strategy? Does it exist? Sometimes you know that it exists and you can't find it. Sometimes you don't know where it exists, etc. Finite games, this is true. Then if it is not turn-based, if it is not win-lose, what happens? Things of this kind. Again, you can show that the kind of equilibrium that I was talking about, you can show for finite games, but perfect information, etc. comes in, so I don't want to go into it. But there is some very nice, interesting way of going about this. Right? But let me end with this, pointing out one more game which you can actually play, and which you can, and it's a very popular and famous game. This is a game called, how much time does that? Maybe 5 minutes? Yeah. Okay, I'll just mention the game. Okay, so this is a famous game called NIM game. So the NIM game is as follows. I have some piles of sticks. Okay. Okay, you play with matchsticks or counters or whatever. Imli seeds, I usually do. So let's say that you got several piles. Okay, here is a pile of sticks. 5 matchsticks. It's not a pile, I laid it out. Doesn't matter. Another pile has 7 and let's say 3. Okay. So some number of piles are there. Each of them has some non-zero number of sticks. Okay. What are the rules of it's a 2-player game. Player takes turn. The 2 players take turns. And supposing you start, what do? You pick one of the heaps and remove some number of matches. Right? You have to remove something. That's all there is. Right? Maybe, for instance, supposing you pick this row or this heap. Right? You could remove 1 match or 2 matches, 3 matches, 4 matches, 5 matches. You could remove all of them. Right? You must strictly reduce some pile. That's all. Okay. Then I get my turn. I pick one row, reduce some number of matches. We keep on going. But what is the winning condition? Well, if it's your turn to move and there is nothing left, then you're gone. Is it clear? 2 players take turns, right? The 2 players take turns, and the allowed move is pick one of the rows and strictly reduce it. You can always bring it down to 0 if you like, but you must reduce. You must do something, right? And if it's your turn and the whole pile is empty, that means you have no choice, you are stuck and you lose. So whoever is the last person to take a match wins the game. Now, think about this game, right? This is already, in terms of the tree picture that I was talking about, you can try to draw the tree. It's big enough, right? Because think about it, right in the beginning you can see, right? I can pick one of the 3 rows. Picking row 1, already in row 1 there are 5 possibilities, right? In row 2 there are 7 possibilities. And row 3 there are 3 possibilities. How many moves that I have initially? 3 plus 7 plus 5. This many, right? I can pick any one of them. So the tree is humongous. So you can't sit and exhaustively search every possibility and do. And this is just for this. Because at the moment you have worked it out, I'll change it and give you a different initial configuration. So it's good to think of it as, okay, somebody has given me a vector k1, km, all ki's greater than 0. That's what I've given you, right? And what is the move? Pick any one of them, reduce. That's all, right? And question is, can you find a winning strategy for either of the players, right? How do you, and obviously it will depend on the numbers that you begin with, right? So you want your notes, so the strategy that you want is something, some function that you can apply no matter what is the configuration, no matter what vector is given. What will the strategy tell you? It will give you a pair. It will tell you one index among 1 to m, and then it will tell you the number that you must reduce. That is what you call a strategy. Now, what you want is a winning strategy. That means what? You must do it in such a way that whatever the other opponent is going to do, you're going to have the last match is yours. That's what you want, right? And I assure you that it is possible. This was solved by Bhutan in 1905. This is another thing that is celebrated its centenary. It's all long ago. Okay, but Axioms of choice is older. So, 1905, this was solved, and he gave a complete solution. And just this little game. By the way, NIM comes from. Don't do Wikipedia, because I found internet says that it's a Chinese game. It's not. It comes from the German word nehmen. Nehmen means to take. Okay. And maybe the Chinese played some games, I don't know. But at least simply because of NIM, I think someone decided that, to call it from Chinese origin. No. So think about it, and think of how you would play and how you would solve a game like this. Because this game, it turns out, has many, many interesting characteristics, and it's representative. In some sense, if you solve NIM games as a class, you solve a whole lot of other games that reduce to NIM in some sense. And there is a very nice book called Winning Ways. Winning Ways for Your Mathematical Plays. That's what it's called, full name, by Conway, Berlekamp, Conway, and Guy, however he's pronounced. But I would really advise you to start thinking of many games of the kind that I was talking about, and the exercise is what I told you in the beginning. What is the exercise? Where is the mathematics in this? Right? I said mathematically speaking. Did we speak any mathematics at all? I don't know. We were talking, I'm using words and there is no formulas, there is no, not even Venn diagrams. Come on. So, I don't know. There doesn't seem to be any mathematics in this. I said theorem, but I didn't write theorem there. So, that's the exercise. Try to find where is the mathematics. Okay. Thank you. I'll also give my email address, so in case you have some solutions for the NIM game that you want to send me. Yeah.
If you
No, I didn't say that. I only said that if you followed some other strategy, right, you would need maybe more than 7 questions. You know, the number of questions that no matter what strategy you use, right, the number of questions that you will ask is greater than or equal to 7. That was it. That was the case. Yeah. By the way, you must also ask, I wanted to, but I forgot, is that we said 100 numbers, right? What if it was 1000? How many questions do you need? Yeah, I said 2 digits. Supposing I say 3 digits, which means between 1 and 1000. 10 questions. Because 2 power 10 is about 1024, right? So 11 questions really. Okay, but yeah. 10 questions you can do. But in general, if it was n, no, I am giving you a number between 1 and n. Log n to the base 2. Yeah. So what we are talking about is that if you, no matter what strategy you follow, the number of questions that you will ask is greater than or equal to log n to the base 2. Yeah.
suppose you're thinking of a number from 0 to 100. Let's give it to 100.
Yeah.
So suppose I want to ask, you converted it into binary.
Yes.
And then I ask whether the first digit from the left side is 1.
Excellent.
You say yes, and then I ask you the second digit is 1, and then you say yes, and then
Yes.
I can skip 2 questions because the next 2 should be 0 because the number is between 0 and 100.
But the point is that you're just giving me the proof that it's log n to the base 2, right? Because n, how do you write n as a binary sequence? Well, log n to the base 2 digits, that many bits you have to write, and each of them can be 1 or 0, and you are trying to find out whether the question that you are asking me is which bit is 1 and which bit is 0. So in the worst case, because whatever question you keep asking me, is it 1? I say no. Is it 0? Whatever, right? I keep asking you some answers in such a way I can force you to ask that many questions.
Yeah, but by mistake you say the first
Yeah,
digit is
mistakes are a different thing, right? Okay, so this is very important that I am assuming in all these things, players who are capable of all, can do all mathematics, they never make mistakes, they are like perfect rational beings according to game theory. So mistakes are a different story. In fact, you can try to find strategies that will tolerate up to 1 mistake, tolerate up to 2 mistakes and so on. That's also fun. And you can actually give answers of that kind. But yes, mistakes are a different story. I'm here assuming that everything you do it without making any mistakes whatsoever. Anything else?
Suppose you're writing the game as a code and making sure the computer never loses. Is there any way of ensuring that the computer never loses other than missing out each and every choice? If the player takes this choice, then loses?
Yes, so that is the backward induction strategy. By working backwards, because the finite tree, I can make that. But unfortunately, that program will take a very, very, very long time to execute. Right? In the case of chess, right? The running time is, huge.
You have to list out each and every case and then
That is the only known thing. That doesn't mean that. I'm saying that Zermelo's theorem assures you that for a finite game of this kind, the computer can always win. But may take a very, very long time, right? So not in your lifetime maybe, right? You start the program, it will in 500 years from now find the answer. Doesn't help. Okay, thank you.
So, I would also like to thank all the speakers of today and all the chairpersons. And I would also like to thank, our office staff, Mr. Vishnu Prasad and his group, who have helped us quite a lot in organizing this. And also thanks to you, all of you, who have, despite the climatic conditions, you have made it come here. Hope you have learned some insights into mathematics. You have, for example, this talk, where is the mathematics? That's an exercise for you. You can think about it. Hope it was something you got it from this one-day workshop, and we would be happy if that reflects in your, once you go back, if that reflects in your pursuit, academic pursuit and habits, we'll be very happy about it. So thank you very much for coming and attending. And there will be a tea break now. At the end of the program, there will be tea. And tea will be dispersed here right now. Please stay here. Please go home safe. Thank you. And participation certificates are also available.